Okay, next up is Ben Knudsen from Northeastern. He's going to invite us into graph braid groups.
Uh, Thank you for the introduction, and thank you to the organizers for the opportunity to speak. I hope everyone online can hear me. So they say that every talk should have a theorem and a confession, and I'm going to start with the confession. I am not a toric topologist. I am not a polyhedral producer. I am a humble algebraic topologist. For those of you who are wondering who the imposter in the room was, it's me. But we have to talk about something for the next 45 minutes. So what I'd like to do is just share some ideas with you that I quite like and that I hope and expect will resonate, to use Alex's word, with some of your aesthetic preferences. And if I'm wrong about that, then we can all blame the organizers for inviting me.
Sounds pretty good. Sounds pretty good.
So configuration spaces. This is what I want to tell you about today. What are configuration spaces? This is what they are. So if I have a topological space X, then I'm going to write Fk of X for the ordered configuration space of k particles in X. So it's just k tuples of distinct points in X. Yeah? No doubt some of you are somewhat familiar with these spaces. And if I quotient by the obvious action of sigma k, then I get the unordered configuration space, which I'm calling Bk. Okay? And sort of the first example, the classical example, is if we're talking about configurations of particles in a surface, if that surface is not the sphere or RP2, then these configuration spaces are aspherical. And so that means that they're classifying spaces for their fundamental groups. The fundamental groups are the only information that's happening homotopically. And if you think about what the fundamental group of a space like this would look like, then you very quickly start drawing pictures like this, where time is going from top to bottom. I start with 4 particles in, I guess here, the plane, and they move in time, and the shape that they trace out looks like a braid, right? And so these groups have been called braid groups in the classical case of the plane in 1 second, and in the case of the surface braid groups. Yeah, Graham.
Can you say in 2 words how you do that?
Oh yeah, great. Thank you for writing my talk for me. So who knows how you prove this? Yeah, so the projection, the coordinate projection from the kth configuration space to the k minus first configuration space is a fibration. This is a theorem, the first theorem about configuration spaces that was ever proved by Fadel and Neuwirth a long time ago. And so inductively, one shows that these spaces are aspherical. Does that make sense to everybody? Great. This is not what I'm talking about today. What I'm talking about today is when the background space X is not a surface, but a graph. And then if you think about it, well, I'm jumping ahead a little bit. Maybe I'll just say 2 words about some motivations for studying these spaces that date to 20 years ago or so, when they were first studied by Rob Greist and by Aaron Abrams. The original motivation for studying these spaces comes from motion planning. So you think about your graph as being like a network of some kind, like the streets of Toronto. And your particles are, self-driving cars, right? And you don't want them to run into each other. So that means that they have to stay inside the configuration space, right? So the idea was to, topological robotics, this is the name of this subfield, a la Michael Farber, to try to understand things about the motion planning problem on a network by understanding the topology of these configuration spaces of graphs. Okay. So this isn't really applied topology. It's like applicable topology, or like trending towards applied. I'm not sure there have ever actually been any actual applications of these, but that's sort of the original motivation. And then starting with this theorem, which is probably the fundamental theorem of the subject, which was proved independently around the same time by Abrams and Sviatkovsky, it turns out that these configuration spaces are aspherical. And so here comes a different reason to possibly care about them. If you like braid groups, which many people do, Here now is a whole new family of braid groups, graph braid groups, the fundamental groups of configuration spaces of graphs. Okay. Now, you might be surprised by this theorem, or you might not. You might not be surprised by it because of the previous example. Like, of course there is spherical, it's true for surfaces. But in light of Graham's question, now that we know how that theorem is proved, you might be surprised by this theorem because the coordinate projections, as soon as your background space X is not homogeneous, you can easily see that the coordinate projection can't possibly be a fibration because the fibers are just different depending on which point you project, right? So the method of proof can't be the same. So the idea behind the proof, and I'm not going to spend too much time with this, but it does get on the board something that we'll spend a little more time with. So what Abrams does is he looks at a subspace of the configuration space, which is what I'm calling Fk with a box. And that's just the largest subcomplex of gamma k. So gamma, maybe I should have said, when I say a graph, what I mean is at most one-dimensional CW complex, right? So gamma is a cell complex. Gamma to the k has a God-given cell structure. And I can look at the largest subcomplex, in the cellular sense, of gamma to the k that lives inside of the configuration space. The configuration space itself does not have a cell structure because I've taken this beautiful cell complex and I've torn out the diagonals, which have nothing to do with the cell structure. So I've ruined the cell structure in doing so. But there's this sort of closest approximation to the configuration space by a subcomplex, and that's this Fk box. What Abrams shows is that it's a deformation retract, at least after subdividing, and that issue is what's hiding in the asterisk, and I will not say anything more about it. And it is also a locally cat0 cube complex. And so from the off-the-shelf theory of cat k spaces, being a locally cat0 cube complex immediately implies being aspherical. So there's some non-positive curvature geometry happening in the background here, which I won't say too much about, but if you like that, then be invited. Are there any questions so far? I knew it was related. Questions so far? Yeah. Yeah, I don't think I have anything like too specific to say about the relationship. It is, but yeah. That is how it is proven, of course, by looking at the link of the vertex. Yeah. Was there another question that I saw their hand go up? No, okay. So let's look at a couple examples. So let's look at the easiest graph that there is, which is the interval, and two particles on the interval. So there's gamma squared. And the configuration space is what I get by taking out the diagonal, right? Now, what is the largest subcomplex of gamma squared contained in the result of removing the diagonal? It's just those two vertices, right? Those are the only cells of the product that are inside the complement of the diagonal. If this isn't crystal clear to everybody, please ask, because we're going to look at more complicated examples in a moment. And of course, as you see, those 2 points are a deformation retract of the complement of the diagonal, verifying Abrams' theorem in this case. Okay. So we're not super interested in the interval. Let's look at a more interesting example. This is the simplest graph that's actually a graph and not secretly a manifold, speaking of imposters. So this is the star graph on 3 leaves. I've labeled the vertices 0, 1, 2, and 3. And so let's just look again at what 2 particles on this graph could look like. And we're going to stay inside of the cellular approximation of Abrams's, this F2 box. So here's an example of a 1 cell there. Well, here's 2 examples of 0 cells, first of all. So when I say 1, 0, what I mean is the first particle is at vertex 1, and the second particle is at vertex 0. So that's the top one. Right? Or it looks like this. When I say 1, 2, that means the first particle is at 1 and the second particle is at 2. And because the movement that takes the second particle from 0 to 2 happens disjointly from vertex 1, there's an edge in F2 box that looks like that. Yeah? Is everybody on board? Okay. What else could happen from 1, 0? Well, instead I could move particle 0 to edge number 3. Right? Or to vertex number 3, excuse me. And those are the only two things that could happen. Those are the only two moves that are allowed. I cannot move the second particle in the direction of vertex 1 without leaving F2 box. Okay? So if you think about this a little longer, what you'll see is that you get this Star of David shape. That's all the cells that there are, which of course is a circle. Okay. So the configuration space of two particles by Abrams' theorem, deformation retracts onto this circle. Which circle is it? Let's just be ultra concrete about what this fundamental cycle is that's happening. What I do is I start with two particles on the graph, and I take turns moving them through the central vertex, right? So I take particle 1 and I move it onto the unoccupied edge, and then I do the same thing with particle 2, and then I keep going. I move particle 1 onto what is now the unoccupied edge, and I do the same with particle 2, and I do it one more time, and I end up back where I started, right? So I am able to allow two particles to orbit each other by taking turns directing traffic through the central vertex. Okay? So if I concatenate those three moves, what Abrams' theorem tells you is that that loop really generates this particular graph braid group. Okay. So this is a simple example, but it actually propagates onto very non-trivial information about these groups and their homology. So I would like you to keep it. Oop, I should not do that. Keep it close to your heart. Sorry, Zoom. Any questions about this? Yeah.
So using that one, you can imagine star graph with k+1 vertices.
Yeah.
K vertices on this one, and do that in this.
Yeah, exactly. So if you have a star graph, which is the cone on more than 3 points, then you can do this in many different ways, right? You can choose 3 of those edges and do this dance and get lots of different classes. And it turns out that the graph braid group for any star is a free group generated by some of these, but there are relations among them. Yeah. Other questions? Okay, let's look at a more complicated graph, K5. So K5 is the complete graph on 5 vertices. There are 5 vertices as shown here and 1 edge between every pair. Where the edges cross in the middle, those are not vertices. I can't draw it without those crossings because it's a non-planar graph. Okay. So we're gonna again try to understand F2 box and thereby understand the configuration space of 2 particles in this graph. I can't actually draw the whole thing, it's too complicated, but let's draw a local picture near the vertex 1, 2, just like we did before, okay? Again, I have these sort of edge moves where I move particle number, where I move one of the particles to any of the possible different vertices I could move to, yeah? And I've drawn those right there. But now what you see is that those 2 moves can be done simultaneously because those 2 edges in the graph are disjoint from each other. So the product of those 2 edges inside of K5 squared lives inside of the configuration space. I'm allowed to move those particles back and forth at will, and they will not collide. And so that's saying that there is a 2-cell, this diamond shape, in F2 box, filling in what would otherwise be a cycle. Okay? If you keep going, of course, there's lots of symmetry around that the situation propagates all around. And this is a picture of all of the cells that are adjacent to the vertex 1, 2 in F2 box. Okay? There's a local picture near that vertex. And there's more stuff, but this is everything that's near. This is the closed star of that vertex, I guess. Everybody on board? So what do you notice about this picture? It's intractable. What else? It's a manifold, yeah. It's near the vertex 1, 2, it's Euclidean, right? So in fact, F2 box is a surface, which you can think about being orientable. It's obviously compact, and it's also orientable. And a fun combinatorics exercise shows you that the Euler characteristic is -10. So the genus is 6. Okay, so Abrams' theorem tells you that the configuration space of two particles ordered on K5 has the homotopy type of a surface of genus 6. So that's another example of a graph braid group. Some surface groups are graph braid groups. Questions? And there are other examples of graph braid groups that are surfaces, and it's not clear if that's just a few sporadic examples or if there's something more systematic going on. So one way to make that question precise will be to ask when graph braid groups or pure graph braid groups are Kähler groups, and we don't know. What do we know about these groups? So one answer to that question is we know everything, because Farley and Sabalka have given us a presentation. So they apply discrete Morse theory to Abrams' cubical approximation, and they get a presentation. But there are two problems. So one problem is that a presentation only gets you so far. Like, it doesn't even get you to knowing whether the group is trivial or not often. And another problem is that the discrete Morse theory presentation is like the generators are critical 1 cells and the relations are critical 2 cells. And then you're like, okay, that doesn't really help me. Where'd the geometry go? Okay. So in some sense, we know everything, but in another sense, we don't know that much because the presentations are, there's a lot of combinatorial overhead that comes with using them. So some specific questions that would be nice to understand of a more geometric flavor would be the following: to describe kernels of various obvious homomorphisms. So for example, there is the inclusion of the configuration space into the Cartesian power. Geometric description of the kernel of that would be nice. There is the projection that we referenced before, the coordinate projection from one configuration space to the next. And a geometric description of that kernel would also be lovely. And you can take your graph and you can embed it into a surface. And so then there's a relationship between graph braid groups and surface braid groups that is often a useful thing to understand. And so a general understanding of the kernel of that kind of homomorphism would also be nice. Yeah? Oh, yeah, yeah. So for those on Zoom, what Alex asked is, are these groups residually anything? Yeah, I don't think that's been investigated. So pretty much any group theory question you might be interested in about braid groups, that is a question that is relevant to these groups as well, and most of them have not been studied at all. Is it known whether classical pure braid groups are residually? But you are telling me that it is. Yes, I agree. Yeah. Other questions? Yeah. I don't know what special means. Yeah, as far as I know that is not. That is not. Thank you. I just wanted to point out about these questions that this is an analog of a theorem of Goldberg's. Goldberg has an exact sequence, a paper called an exact sequence of braid groups, and this is exactly the analog of that. This is an analog of the theorem of Fidel and Neuwirth that I referenced earlier, and there is one result in this direction where the surface is the plane. So for planar graph braid groups on a Maciejczek have nice geometric presentations that quotient down predictably to the ordinary presentation of the braid group. Okay. So what about homology? And actually, we're going to stay with homology for the rest of the talk. I'm going to tell you a theorem that I proved with my collaborators, and my reason for focusing on this theorem is it will allow me to sort of point to various interesting aspects of the homology of these spaces as we sort of think about what the theorem says and why it's true. But to state the theorem, I have to give you a definition of a family of graph invariants. So they're called Ramos numbers, and there are countably many of them. So fix I, which is like the homological degree. Then the ith Ramos number is called delta. And what it is it's the largest number of connected components that you can get by removing I many vertices from your graph. And they have to be like actual vertices. So they have to be essential vertices, which means that their valence is at least 3. So I'm not allowed to remove bivalent vertices. That's like cheating. Okay, so once again, I fix I, that's my homological degree in a moment, and I choose that many vertices of valence at least 3, and I remove them topologically from the graph, not combinatorially, topologically, and I look at the number of connected components that I have. This is similar to something that came up in Alex's talk. He wrote down the cut polynomial. So this is a similar kind of thing. Okay, are there any questions about the definition? Okay, so what the theorem, which is joint with Young-Hee Ahn and Gabriel Drummond-Cole, says is if you choose your favorite coefficients, doesn't matter what field you choose, and let's look at homological degree bigger than 1. The degree 1 case is completely understood, but is not a uniform statement like this. And if we look at a connected graph that has an essential vertex, so it's not a manifold, then the Betti numbers over that field are eventually equal to polynomials in the number of particles, k. So I'm fixing the homological degree I, and I'm viewing the Betti numbers as a function of the number of particles, k. And the theorem says that that function is eventually equal to a polynomial. And moreover, the exact degree of that polynomial is delta minus 1. This Ramos number is telling us the degree of the polynomial. And we can say what the leading coefficient is. The leading coefficient is this. So 1 over Ramos number minus 1 factorial. And then what I do is I sum over all of the W. Remember, W is a set of I many essential vertices. I sum over all the possible W's that maximize the number of connected components. So all of the W's that achieve the Ramos number when I remove them. And then I take a product over each vertex in W of the degree of the vertex minus 2. That's a typo. That should say D of V, excuse me. So whatever, it's a number. Are there any questions about what the theorem says? Yeah. Sorry, could you speak a little louder? This should be a V. Yeah, that's a typo. Thank you. For Zoom people, the question was, is this number? Oh, I don't even think it can be seen. Oh well. It was about the typo. Other questions? Okay, so again, just big picture. For any field, the ith Betti number as a function of the number of particles is eventually equal to a polynomial, and the degree and leading coefficient are expressible in terms of graph invariance. Okay, so let's just very quickly look at an example. So here are all the possible degrees. We're going to look at K4, the complete graph on 4 vertices. I can look in degree 0, 1, 2, 3, 4, or greater than or equal to 5. And there's a lot of symmetry here, so I don't need to think about which set of however many vertices I take out. There is the result of removing that many vertices. Those are the Ramos numbers, so I just count the number of connected components. And here are the asymptotic Betti numbers. In H0 it's just 1. In degree 1, our theorem doesn't tell you what it is, but Ko and Park calculated H1 completely. So they give you the answer. In degree 2, 6k is the asymptotic Betti number, the leading term, in other words, of this polynomial. Degree 3, it's 2/3 of k cubed, and degree 4, it's 120th of k to the 5th, and above that, it's 0. Yeah.
Back a slide, quick question. So in general, there's going to be torsion, right, in these homology groups.
I will address
Yeah.
torsion later.
Right, but before, but on the other hand, this asymptotics and the long-term behavior or stable behavior does not depend
Yeah,
on the field.
that's right. So-
there is something going on here.
Yes. So I guess you had the microphone, so I don't need to repeat it. You've spoiled my talk. Thank you very much. Not really. So yes, the asymptotics of the Betti numbers are independent of the characteristic. So the way that I encourage you to think about that is that the homology is asymptotically torsion-free. So as you know, by the universal coefficient theorem, if the Betti numbers, if we assume reasonable finiteness, the Betti numbers are independent of the field, that's the same as saying the homology is torsion-free. So that's not literally true, and I will give you an example later of non-trivial torsion, which is the only known example, spoiler. But asymptotically, all of that interesting torsion, however much there is, drops out. It grows slow, and so it doesn't contribute to the asymptotics. Yeah, that's a corollary of the theorem. Yeah, good question. Other questions? Okay. So let's try to prod in a little bit to this result. First of all, a question you might have is why do we have eventual polynomial growth at all? And the theorem I'd like to remind you of is a classical result of Hilbert's, which says that you get eventual polynomial growth when you have a finitely generated graded module over a polynomial ring. That's the Hilbert polynomial. And there's a bound on the degree also. Okay, so what do polynomial rings have to do with anything? Given an edge of the graph, I'm going to tell you a way to increase the number of particles on that edge continuously. Okay. So there's my edge, and there are my particles on the edge. There's lots of graph that happens outside of the dotted picture, but right locally on that edge is just those two particles. And what I'm going to do is I'm going to replace that subconfiguration. And it's important now that I'm talking about unordered configurations. I made that transition without saying enough about it probably. The theorem, the homology theorem that I just stated, is about unordered configuration spaces. Okay. So I have these two particles in this subconfiguration, and I replace that subconfiguration with the collection of averages of endpoints and consecutive particles. It's a little bit of a mouthful, so this is the picture. I take the leftmost endpoint and the first particle, which are in the same place, and I average them. And I take the first two particles, and I average them. And I take the second particle and the rightmost endpoint, and I average them. If I do this, then I increase the number of particles on that particular edge by 1, and it's continuous. You can check. Okay. So this is a way, given an edge of the graph, to increase the number of particles in a configuration in a continuous way. So in other words, it is a map from the kth configuration space to the k plus first configuration space. And if you think about it, what I am doing on different edges, it doesn't talk to each other. And so these maps commute with each other. And so there's an action of the polynomial ring on E many generators, where E is the set of edges of the graph, on the totality of all configurations in the graph. So I just take the disjoint union of all the configuration spaces, and I view that as a graded space. And there's now an action of the polynomial ring generated by the edges on the homology of that graded space. Everybody on board? Any questions? Yeah. Yes, absolutely. So in the example here, one of the vertices is at an endpoint. And so the recipe is take the average of the first endpoint and the first particle. And if they're in the same place, the average is just the same thing. And that's why the leftmost particle in the result subconfiguration is also at the endpoint. Yeah, good question. Other questions? Okay, so there's this action of this polynomial ring, and what we prove is that the homology is finitely generated over this polynomial ring. And so the theory of the Hilbert polynomial applies to give eventual polynomial group. And so a perspective on this result that I would like to advertise is the perspective of homological stability. So classically, the configuration spaces of a manifold with some reasonable assumptions on M, the manifold, the homology is eventually constant. That's what's called homological stability. Constant is a function of K in fixed degree. And at least if it's an open manifold, this is a theorem of Macduff, and we can think about Macduff's theorem as saying that the homology is finitely generated over a polynomial ring on one generator, where that one generator acts by adding a new particle very far away, near the boundary, say. Okay, that's homological stability. For ordered configuration spaces, the asymptotics of the Betti numbers are that they are eventually polynomial, or if we think of them as representations of the symmetric groups, and we work rationally, they are eventually constant, one character at a time, one irreducible representation of the symmetric group at a time. That's the theory of representation stability of Church, Ellenberg, and Farb. And that is equivalent to finite generation over the category Fi of finite sets and injections. So there's a sort of a general philosophy in this world of stability phenomena that says that certain asymptotic behavior of homology, that's the stability phenomenon, should be equivalent to finite generation over some algebraic gadget that acts on your homology. Okay. So in our case, we're talking about configuration spaces of a graph. The behavior is eventual polynomiality, and the thing acting is this polynomial ring generated by the edges. Okay. This is some context. Of course, the thing that goes in the bottom row is ordered configuration spaces of the graph, and this is joint work in progress with Nick Vavrikov. We are in the process of proving that the Betti numbers grow like polynomial times factorial, times k factorial. So they're big. Betti numbers of ordered configuration spaces of a graph are very large, and this makes them difficult to deal with often. Few computations have been done because the Betti numbers are too big. In terms of what is acting, let me not get into it. I'd be happy to tell you about it later. Any questions before moving on? So another question you might have is, why is that the degree of the polynomial? Where do the Ramos numbers come from? So let me tell you why the degree must be at least that. So if we want to bound the degree from below, we should just point to a submodule that definitely does have that growth. And then that will be a lower bound on the degree. Yeah. So this is where we're going to go back to the second example we saw of the star graph with three edges. So what we saw there is that the configuration space of two particles in a star graph with three edges had the homotopy type of a circle. And so if I have an essential vertex in my graph, I have at least three edges coming together. I can choose an embedding of that star graph into my big graph, like so, and push forward that degree 1 homology class. And we'll get what's called a star class. That's in degree 1 homology of two particles on the big graph, but then I can stabilize by adding particles stationary on other edges and get a degree 1 class in any k. Okay? And if I have a set W of essential vertices, then I can just do this at each one of those, choose an embedding of a disjoint union of star graphs, one at each of those vertices, and do that dance of two particles at each one of those vertices at the same time. And that will give me a torus, S1 times S1 times S1 times S1, a W-dimensional torus, and I can push forward the fundamental class of that torus into homology and get a homology class in degree size of W. Okay? So this most basic example is a way of generating easily understandable homology classes. Okay, and so what we're asking about is a module over this polynomial ring. And so what we're interested in is what is the submodule of homology generated under that polynomial ring action by one of these toric classes. So I have a homology class, I have an action of a polynomial ring, I can generate a submodule using that one class. What does it look like? The observation is that the action of this polynomial ring on that W torus, which I'm calling alpha, factors through a predictable quotient. So the thing acting is the polynomial ring generated by the edges of the graph, but the action on this W torus actually factors through the quotient where I identify two edges if they are in the same connected component after I remove W. Okay? That is like a little bit of a mouthful to say, but actually what I'm saying is completely obvious. So let me show you a picture that will tell you why it's completely obvious. There's a graph, that's theta 3, the theta graph. And let's say that the class alpha we're talking about is where two particles are orbiting each other near the right-hand vertex. Yeah? Now, E1 times alpha is the class where the third particle is sitting on edge number 1. E2 of alpha is the class I get by instead putting the third particle stationary on edge number 2. And because I have a path from edge number 1 to edge number 2 that avoids the vertex that's occupied, E1 times alpha is equal to E2 times alpha. That picture that I've drawn is a homotopy and therefore a homology between those two things. And similarly, that same thing is equal to E3 times alpha. Okay? So because E1, E2, and E3 are in the same connected component after I remove the vertex that's occupied, their action is the same on this particular homology class. Is everybody on board? Are there any questions about that? Okay. So that's saying, what were we illustrating? Let's just remember. That was saying that the action of this polynomial ring on this toric class factors through a predictable quotient where I identify edges in the complement of W. Sometimes the action factors even further than that. So there's a relation in homology of this graph theta 3 that says that the class where two particles orbit each other on the left is the same as the class where two particles orbit each other on the right. That's not obvious, it's something you calculate. It's called the theta relation. And what that tells you is that in this sort of theta graph with a tail, not only do we have E1 alpha equals E2 alpha equals E3 alpha, we also have that those three things are equal to E4 alpha, because I can take the star class at the right-hand vertex and flip it over to the left-hand vertex using the theta relation, and then at the left-hand vertex, E1, E2, E3, and E4 are in the same connected component of the complement. So this theta relation is like a sneaky way for extra relations to crop up. Okay? But what we prove is that this doesn't happen some of the time. So we prove that if your set of vertices maximizes the number of connected components, then there is some toric class, alpha, so that the submodule of homology generated under the action of a polynomial ring is exactly free on this specific quotient of the polynomial ring. Okay? And that immediately gives a lower bound on the degree because it tells us that the rank of homology has to be at least the rank of this free module generated by this certain quotient, and it's easy to see what the asymptotics of that are. That's just a balls and boxes formula. Okay. Questions at this point? Oh, balls and boxes formula. So the formula for the rank of a graded polynomial ring in a particular degree. Yeah. You know, like k plus n minus 1 choose n minus, that kind of. Yeah. Okay. Other questions? All right. Yeah. Oh yeah, that's a good question. There's a really great Stewart exact sequence around here that I don't really have any time to tell you about, but I'd be happy to tell you about afterward. Yeah, that kind of thing is very relevant, and I won't say anything more about it. Yeah. Okay, so in the last few minutes, let me just wax philosophical a little bit and point to some features that I think are interesting. So this idea of generators and relations is kind of floating around. We have these particular geometric generators that happen at particular vertices and are controlled by a star graph with 3 edges. And we have these relations, like this theta relation I wrote down, that's saying how they behave. So what that motivates is a kind of universal generation problem. In a particular homological degree, do you get all classes in the homology of configuration spaces of a general graph by pushing forward classes from a small list of atomic graphs, like the star graph on 3 vertices. In degree 1, this is known to be true. So what Cohen Park prove is that the circle and the star graph are the only generators you need. All homology comes from those 2 graphs. What I prove with Byung-hee is that in degree 2, as long as we're talking about planar graphs, you only need 1 extra generator, which is a theta graph with 4 edges. Turns out the configuration space of 3 particles in that graph is a surface of genus 3. You wouldn't know. But for non-planar graphs, there are other generators that we don't understand. But what our theorem is saying is that asymptotically, there's only 1 generator, which is the star graph. So all these other, it's a little bit of a dark matter problem, or like, I guess it's a light matter problem. We only understand the dark matter. We only understand the thing that dominates in the limit. And there's all this other unstable stuff that grows slower that we just don't understand. Questions? Yeah, Graham. That's a great question. So a theorem that didn't make it onto the slide, but I will now say, which is due to myself and Eric Ramos, proves that there is a finite list in fixed homological degree, assuming some reasonable categorified versions of facts about well-ordering theorems for graphs. So like a categorification of the graph minor theorem and a categorification of Robertson's conjecture. Those 2 things together imply that there are finitely many generators in fixed degree. Otherwise, it's totally unclear. Yeah, so their work is about this categorified graph minor conjecture, which is still a conjecture. And my work with Eric is about a categorification of Robertson's conjecture and how it implies this universal finite generation in fixed degree. Okay. Another interesting angle is torsion, which Alex brought up earlier in the talk. So as Alex was saying, this asymptotic Betti number is independent of the characteristic of the field. And so asymptotically, there's no torsion. Or in other words, any torsion has to grow slower, has to generate a submodule of homology with slower growth than overall homology. But there is torsion. So again, Cohen Park's seminal work on H1 shows that the presence of 2 torsion in H1 is equivalent to non-planarity of the graph. So there's torsion detects planarity of the graph. And this is actually very easy to see with what we've established so far. So K5 is, half of the examples of non-planar graphs that there are. The other is K33. What we can see immediately is that there must be 2 torsions. So how do we see that? At the leftmost vertex, this arrow is supposed to indicate that I have a star class where 2 particles are orbiting each other by taking turns passing through that vertex, using the 3 blue edges. And that theta relation, remember, tells me that the star class at one vertex of a theta graph is equal to the star class at the other vertex of the theta graph. So what that means is whenever I have an embedded theta graph in a big graph, I can move the star class from here to here. So if I do that using the theta graph that's in blue, that blue is an embedded theta graph inside of K5, I can move the star class that's at the leftmost vertex to the top vertex. And if you keep track of orientations, it's actually equal to the star class that's orbiting the other way. That's where non-planarity comes in. And so if you do this all the way around K5, you end up back where you started, but with the opposite orientation, because you've done it 5 times. And so that tells you that alpha, this star class, must be equal to -1⁵ times alpha. And it's not 0. You can prove that it's not 0 easily, and so it is 2 torsion. And this example is the only example that is known of homology of torsion in the homology of graph braid groups. And there are no examples known of torsion in the homology of pure graph braid groups. So this is a giant mystery, which has led some people, or I think some people have conjectured this. I haven't. I think it's not supported by calculation, that the homology of graph braid groups has no odd torsion at all. How could there be any? We haven't found it. And if the graph is planar, no even torsion either. People also conjecture that the homology of ordered configuration spaces has no torsion at all. But this is just wildly out of reach of any computations that we have. And as Alex mentioned, asymptotically, the conjecture is true. So any torsion must arise from exotic classes that we don't understand that have slow growth. A more achievable conjecture that my student is working on, that I will go so far as to conjecture, says that any torsion from the configuration spaces of the plane restricts trivially under a planar embedding. I think that's true. So let me just finish. I'm a minute over time. Sorry about that. Let me just finish by saying that there's this circle of ideas about generators and relations and torsion and growth. All of it is interconnected, and we understand some compelling pieces of it, but we definitely don't understand everything. And a concrete problem that I'll close with that would shed some light would be to understand the secondary asymptotics of homology, which would be getting at like, what is the next fastest growing generator after these tori? I think that would be really interesting. I have no idea. So thanks.